Hello, Chemistry 10HH students. This is Mrs. Altman. We are on video number 41, Bonding, Part 1. We are now in Chapter 8 of your textbook. Here are our objectives for today's video. Pause here, just a rough sketch of the picture is completely fine. So as you may have deduced from the title of this video, we're primarily going to be talking about bonding for the rest of this chapter. So we've already learned that there are two types of bonding, covalent bonding and ionic bonding. The first place that we really saw this was when we talked about nomenclature. So you learned that type 1s and type 2s, those are ionically bonded, and that type 3s are covalently bonded. And all of that is still true, but there is a little bit more subtlety to that as well. So then within covalent bonding, you can have things that are completely nonpolar covalent. So that would be the top left image where the electrons are shared equally between two different atoms. And then there's polar covalent. So polar covalent is still covalent, but it has some ionic character. And when I say ionic character, what that means is a portion of that molecule has a partial positive charge and a portion has a partial negative charge. Those little symbols there, that is the Greek letter delta. I know it is a Hebrew letter too. You'll have to remind me what that is. All that means is a partial charge. Whereas ionic bonding, and you've probably noticed I put bonding in quotes because technically it is not bonding since there is not constructive overlap of atomic orbitals, but it is such a strong Coulombic force, and a Coulombic force means an attraction between differently charged electronic particles. It is such a strong force that we call it bonding, even though technically it is not. We're going to be focusing on covalent bonding, whether that be nonpolar or polar covalent, for really the remainder of this chapter. Pause here. So when we talked about our redox, like assigning oxidation states, we talked about electronegativity before. It's going to be even more important in this chapter. So we already learned electronegativity increases across a period and decreases down a row. Fluorine is the most electronegative, followed by oxygen, followed by nitrogen. And this second rule is going to dominate things in the first rule. So for example, oxygen is more electronegative than chlorine. Nitrogen is also more electronegative than chlorine. Other than that, I'm not going to expect for you to know exceptions. Aside from this third one that's listed here, carbon and hydrogen are approximately equal in electronegativity. While if you actually look up a table of values of electronegativity, you'll see that there is a little bit of a variation between the two of them. The bond length is so short, and that makes it such that the overall bond is nonpolar, which is really the purpose of knowing electronegativity. So think of carbon and hydrogen as being approximately equal, and you do just need to memorize that. It will make your life a whole lot easier if you do. Pause here. All right, so I'm going to give you a sort of like cheat sheet for how to do this if you hadn't already figured it out. Something is going to be covalent, which is the same thing as nonpolar covalent if it is two of the same things bonded to one another, or if it's carbon and hydrogen. If you have something that is two different nonmetals that are not the same thing or not carbon and hydrogen, it's going to be polar covalent. And then if we have a metal and a nonmetal, it is ionic. So A, that is covalent or polar covalent. B, that is, I'm sorry, I just said polar covalent. I meant nonpolar covalent. So A is covalent or nonpolar covalent. B is polar covalent. C is ionic. D is polar covalent. And E is nonpolar covalent. Pause here. So we can actually have polar bonds without having polar molecules. So you know a bond is polar is if there is a significant difference in electronegativity. So if you've got two different nonmetals, you'll have a polar bond, and then how polar it is going to depend on how big of a difference in electronegativity it is. But you can have polar bonds without having a polar molecule. So this whole chapter, we're going to talk about the geometric 3D structure of molecules. For right now, you don't need to know how to do that just yet. We'll get to that in a later chapter, or not later chapter, a later video. But if you have a symmetric placement of polar bonds, the forces actually cancel out and you will have a nonpolar molecule. So you have to have asymmetric placement of polar bonds around, we'll typically have something called a central atom, which is one that's just in the middle, hence the term central atom. So if you have asymmetric placement of polar bonds, then you will have a polar molecule. And the reason why we care about this is because polar molecules affects things like the intermolecular forces, which we saw was pretty important with the gases chapter. And the last chapter of the year we do, you'll see that it's even more important. Pause here. So if you take a look at this picture, you'll see that there are two CO bonds, and both of those bonds are polar, but they are symmetrically placed around the carbon, which is the central atom, the atom in the middle. So the forces actually cancel out, and we have an overall nonpolar molecule. All right, that is all for tonight's video. Thank you so much for watching, and have a great night.